agree that. So one nice consequence of this is that being isomorphic is a symmetric relation. So a nice consequence. You know, if G is isomorphic to H, now remember, by definition, this means that there exists an isomorphism, G to H. But this implies that, in fact, H is isomorphic to G. And that's what you'd want, right? I mean, if there's any sort of reasonable notion of two groups being the same, it shouldn't depend on which one you call G and which one you call H, right? It should be a symmetric relation. And maybe this reminds you of something that's called a symmetric relation. You guys seen this before? So we also know that, well, I should make this, you've also seen, we also know that G is, of course, isomorphic to G, because what's a nice isomorphism?
Identity.
The identity, great. Use the identity. How do you spell identity? Identity map? I can spell identity. So this is called a reflexive relation, if you have that the relation holds between its, any element and itself. What's the last one I'm going to write down? Also a transitive. Okay, so let me write this down. We're going to come back to this now. Equivalence relation, of course, and we'll come back to this notion. I just want to mention it now. We're going to come back to this in probably next week. But it's also the fact, also true that if G is isomorphic to H, and let's say H is isomorphic to K, we get G is isomorphic to K. So yeah, let me give these names. This is called a symmetric. So you say that the relation being isomorphic is symmetric. This is saying that it's reflexive. Oops. And then this one is saying that it's transitive. And so, yeah, I'm just going to mention this. I'm not going to say more about this. We'll get into, we're going to do a whole kind of lecture on equivalence relations, but let me just say it now that this is an equivalence relation. So how many people have seen this word before in their other classes? Okay. So still a little hazy maybe. We'll say more about that when we get to cosets of a group and of a subgroup. I just want to mention it now. It makes sense to talk about now. Okay, so some examples of isomorphism we've already seen. So some examples of isomorphism. Well, let me actually give you an example that's also relevant to your homework. So recall Zn star dot. So this is notation we use on your homework. I want to make sure you guys remember what this is. So this means the non-zero numbers between 0 and n minus 1 under multiplication. Well, non-zero, right? So 1, 2, 3, 4, up to n minus 1. Well, I'm not sure if we explicitly talked about this or not, so that's why I'm doing it now. This is a group, this forms a group if and only if n is prime. Not sure if I explicitly wrote this down yet. So this is a group, this forms a group under multiplication, that's what this is. Under usual multiplication, or modular multiplication. Multiplication mod n. And only if n is a prime. Okay? So I'm not sure if I wrote this down yet, so now you know. So we'll usually write ZP. So remember, Zn with addition is always a group, right? If you pop out 0, then you sometimes get a group under multiplication, but you have to have n to be a prime. Let me just give you an example. Well, you guys know what primes are, so let's just take, how about 5, e.g. z5 star dot. This consists of, so what are the elements of this guy? 1, 2, 3, 4, there's 4 of them. And you know, it's multiplication mod 5. So what's the identity element? It's a group, it should have an identity. 1. So now what's the problem? When n is not prime, you always have the identity, right? So the problem must be in the inverses. And that is the case. I'm not going to say too much about that. When you're prime, everything's got an inverse. We can actually just explicitly talk about this now, right? So 1 is the identity. I don't know, what's 2 inverse? What's the thing that multiplies 2, right? We want 2 times x to be equal to 1 mod 5. 2 times, right? So what is x? 3, right? Well, that's nice because what's 3 inverse? 2. I mean, one guy is the inverse of the other is the inverse of the one guy. And then what's left? What's 4 inverse? What is it?
1.
Well, 4 times 1 is 4. Right? We want it to be 1. So what times 4 is equal to 1 mod 5? 4. It's itself. Right? Is that clear? Right, we want, again, 4 times x to be 1 mod 5. That's the condition we're trying to check, right? And yeah, 4 does it, right? 4 times 4 is 16. So again, 4 is its own inverse. Now, okay, so I mean, we've almost written out the multiplication table here. Now, while I'm here, let's actually talk about why Z6 maybe is not a group. So if I take Z6 under multiplication, this is not a group. So since, so what is Z6 star? It's 1, 2, 3, 4, 5. So, you know, you might guess the guys that aren't going to have inverses or have something to do with the divisors of 6, right? Because it's a condition on the primality of the number. So 2 does not have an inverse, since e.g. 2 has no inverse. Right? If I want to say, what's 2 times x, can I make that 1 mod 6? There's nothing. I mean, you can, if you like, go through them all. This has no solution. Okay, so that's just an aside here. These are not nice objects, but when your n is prime, you're good. You have a group. Okay, but is this guy something that we know? It's a group with 4 elements. You know, the question is it isomorphic to something we know? What I want to ask is Z5 star isomorphic to anything else we know? Another familiar group. And how many elements does the familiar group have to have? This has 4 elements, so you better look at groups with 4 elements, right? It can never be isomorphic to a group with 10 elements because it has to be a bijection. And any guesses? So, you know, you guys sort of know 2 different groups with 4 elements. Yeah, shout it out.
Does it map to its inverse?
Well, I need to find another group that it maps to.
Okay.
I mean, this guy is always isomorphic to yourself. Oh, you're saying, is there another isomorphism besides the identity or something, maybe? Okay. That's actually a question you can ask. It's actually the last problem on your homework then. That's a little bit of an aside. But when I say isomorphic to another group, I got to find another group. So again, you guys, I think you have sort of two to, yeah, so which one?
Z4 with addition.
Z4 with addition, okay, great. So is it true that it's isomorphic to Z4? That's a guess. So I mean, you guessed, I mean, in some sense, that's how you have to do it. So what about Z4 with addition? Okay, so how do we verify that these would be isomorphic? So let's do it the kind of get your hands dirty way first, and then I'll show you a slicker way that might be relevant for your homework. So if I claim that something's isomorphic to another thing, I have to find a bijection that satisfies the property, right? So to verify that, prove the claim, or to show that Z5 star dot is isomorphic to Z4 plus, we need, can I call this G and H just so I don't have to write? We need a bijective F from G to H, satisfying that condition. F of, say, M times N. So this is literally times now, right? I mean, because it's times. So this should equal what? F of M. What's the operation over here? Plus. Okay, so these groups are small enough we can almost write out all the possibilities. Now 1, 2, 3, 4 is this guy, right? And then we've got 0, 1, 2, 3 here. So we'll say more about this, I guess, in a second. Maybe we'll break first. But I mean, at this point, at the very kind of basic level, we just need a bijection, and we can check that it actually satisfies the conditions, right? So I don't know. Can you guys feel where the identity has to go? So it's going to turn out that any isomorphism is going to send the identity in the one group to the identity in the other group. That's a homework problem. Okay? So, fact, F of the identity in G has to equal F of the identity in H for any isomorphism. So if there was an isomorphism, you'd need this. Now, where should we send 2? Well, bear with me. I claim that I can send 2 here. Okay, we can check this later, but I'm kind of maybe holding your hand a bit here. So if we send 2 to 1, though, where do we have to send, well, what's forced now? 4 is forced, because 4 is 2 times 2. Right? So if I send if f of 2 is 1, then I need f of 2 times 2 to be equal to what? F of 2 plus f of 2, which is what? 1 plus 1, which is 2. Okay? That's forced. Oh, thank you. Yeah, wrong arrow. Thank you. But this does force the other guy, of course, because this guy is the only one left and has to go the only one left, right? So, okay. So we've almost checked the condition. Let me finish this here. This is 1 plus 1 is 2. So we've almost checked all the conditions. I'll let you maybe check the details, but. So we still have more to check, right? This is sort of the guess that you'd make, and then you'd have to check a couple other conditions, right? You have to go through all the MNs. So it's a little bit tedious. But here's a slicker way. So slicker proof. Well, I'll say you can check that this works. And again, that means that you have to check this condition for all the pairs over here. So, well, 4 choose 2. There's 6 things you got to check. Okay? But the slicker way is as follows. What do you guys know about Z4? So it's an abelian group, but it's more than that. It's a cyclic group, right? Recall that Z4 is cyclic. And the other thing we know is that all cyclic groups of order 4 are isomorphic to it. This is from last time, right? Are isomorphic to Z4. Remember we proved that on Tuesday, last Tuesday? So it's actually enough to show that Z5 star is cyclic. Right? Because if we can show it's cyclic, we know that every cyclic group of order 4 is isomorphic to Z4. So it's enough to show that Z5 star under multiplication is cyclic. And that's sort of easy, right? Because you just find a generator. What's a generator? Yeah, 2 is going to work. Indeed, if I take the element 2 inside of Z5, what do I get? I get 2 to the first power. What's 2 to the... So 2 squared is really 2 times 2 now. 2 cubed is really 2 times 2 times 2, which is 8, but which is 3. So this is 2 to the first. This is 2 squared. This is 2 cubed. What's 2 to the fourth? 16, which is 1. That's it, right? That's the whole group. So G is also cyclic. QED, it's got to be isomorphic to Z4 under addition. And that's going to be a hint for your homework. I mean, you got 4 groups to compare, and you probably don't want to go, I mean, it can't hurt to go through this. Maybe you learn something, but you know, this is really the kind of more top-down way. So, okay, so let's take a break till